So I will talk in English. The talk will be about integration of updated laser scans into as-built point clouds for urban digital twins. So what is it about? So we talk about urban digital twins, and we talk about this because of a reason. If you see, this is part of Munich, and Munich changes. Cities and infrastructure permanently change. We have construction sites, we have changes in the infrastructure of the city. This might be that there is some construction site. This might also be that there is a building demolished or that the building gone. So we need to have information that tells us this. We need information that gives us the current state of the city to tell us what might change. And one example also is the Königsplatz, which is right here aside, that is a hotspot for various events. So this is used to do lots of different events, and we always need to have an accurate and current a model of how it looks like to be able to make new events at this place. So we need accurate and up-to-date information. How can we generate this information? Well, generally we use laser scanning. We use laser scanning, meaning that we take several laser scanners, one of those maybe, there exists a various bunch of laser scanners that remain static or that also move. That can move on land, so we place them on a car, we place them on our back, so we use a backpack mobile mapping system to go around, large ones, small ones, cheap ones, high expensive ones, or we just take them in our hands and go around and map the environment. And in the end, how is the idea? Well, the idea is we have some kind of city and we want to document the current state of this city. So we take a laser scanner, we could do this permanently, as said before, so we place it on some site and then we measure everything that we can see from this. Or we build this on a car, go through the streets and map everything. Or we take it in our hands, as said before, and then we have more possibilities to go narrow to the buildings. We can go other pathways, and we might be able to document things that are not seen from the street. Or we document from above. We use UAVs, we use airborne laser scanning or other sensors to just document from other sites. So we have different possibilities, different sensors to use, and then also different possibilities to merge those point clouds, because they shall all be merged to, in the end, have a state-of-the-art and up-to-date information about the city. And for airborne laser scanning, it might look like this. So we have a point cloud where we have everything mapped quite good from the top, but we might have some occlusions seen from the street. So if we add on mobile laser scanning data, we have much better documentation of the city and much better information. So we have those kind of information, and they also need to be merged somehow, and they also, I will point out later a bit, is they need to be geo-referenced. So they need to be in a consistent reference frame that the geodesists do. So how would this look like? If we look into a point cloud, here is a point cloud from a mobile mapping system, from a car-based mobile mapping system. Some path through the street, and you can see lots of points that are outliers, lots of points that document stuff that we are not so interested in, like people, like cars, like other informations. And you can see also lots of points flying in the air. And so there is a lot of disturbing information that we are not interested in. We want to document the infrastructure, the street, construction sites, buildings, and also on, all this on. So we need to somehow use this data and pre-process this data to only get the relevant information. Another example, if we go with a bicycle mobile mapping system, and this is now not seen from the street, but seen from the pathway where the bicycle runs. So we have a different perspective, different information, different outliers, and so on, and this needs all to be merged in the end. Or the video you already saw before, this is a backpack system. So a colleague of mine used a backpack system and just walked across Königsplatz. So we have lots of point clouds that we somehow need to merge and where we need to extract the relevant information. And point clouds might also be only one part of this whole process. You see up on the left the point clouds, but there might also be other information like images, like 3D models, like lane models, and all this can be merged. And here's one example where also a chair of geoinformatics and other chairs were involved, where we built the dataset TUM2Twin, where we have perfect documentation of TUM using different kinds of datasets. And in the end, we have such kind of a model that combines all these data sets. And we can use this for various applications that you are all the experts in, like we can derive facade segmentation, we can do LoD2 reconstruction, we can make solar potential analysis. So this provides a lot of benefit we can take from this merged kind of data. But one really important aspect is this all needs to be georeferenced and stated in a good absolute reference frame so that they can all be merged, those data sets. We in Munich have 25,000 official survey points that all this data needs to somehow be georeferenced to. So this is an important aspect. So in the end, if we say we need accurate information to update maybe urban digital twins, we somehow have different challenges but different possibilities if we talk about point clouds. First of all, the urban digital twins need to be up to date. So we need to do recurrent scanning. So do this all and all again. We can use point clouds for this or laser scanning because we can document the infrastructure as is quite good. And this is also quite efficiently if we use mobile platforms. But we have problems like those suffer from various error sources. So we have several error sources that hinder a direct integration of those data into the digital twin. We have irrelevant and distracting information in those data sets, like traffic, like people, like vegetation, that we might not be interested in. So this all needs to be tackled if we design an approach to integrate this into the digital twin. And all the different kind of data sets are not consistent. We have different reference frames, we have different locations, different orientations, and all this needs to be integrated somehow using algorithms that assure an accurate registration. And out of this, we try to tackle 3 questions that I would like to address today, quite shallow, each of those questions. So how can we determine the uncertainty of the point clouds? How can we align the laser scans, although we have this information that we are not interested in, although we have outliers and stuff? And how can we also align the laser scans into LoD2 City Models? So it's not only about we want to register or georeference into existing point clouds, but we also want to georeference in LoD2 City Models because this also brings in several benefits. And this is what I would like to tackle here on a short, not too deep. So the first question could be, how can we determine the point cloud uncertainty? Because we need to know the uncertainty to afterwards to be able to decide which information to trust and which information not to trust. So basically, we have several error sources that we could need to tackle at laser scanning. So I said I will just give you an impression of what this means. This means we have a laser scanner that has misalignments, that shoots the laser beams into the wrong direction. Then the laser beams crosses the atmosphere, also brings in uncertainty. Then the laser point hits the object based upon the reflectance. We have good or bad reflectivity. Then we have the measurement geometry. This also introduces errors, and then we need to georeference. All this brings in uncertainty, and we somehow need to validate this uncertainty to be able to say, okay, I trust this point cloud or I do not trust this point cloud because the given information is more accurate. And this is now for a static laser scanner, but I will skip this, if we move the laser scanner, we have additional drift effects and some other things because the positioning of the mobile platform is not accurate. So this means in reality, we have a mobile platform. The red path is where it directly walked through or where it went. But the system tells us it was a green lane or it was a blue lane just because of drift effects. And this is really important, as you will see afterwards, because we need to somehow take this into account. If we say we have a mobile laser scanning system that walks across the street and we now want to register and georeference the data, we need to tackle the fact that we have drift effects. And one totally different application, but this is quite easy to, or I can quite good illustrate this here, is we also, for example, do rockfall monitoring for certain sites. We use a backpack system. We walk across the Höllental climb, a climb several hundred meters long. We go forth and we go back. And what we do then afterwards is we see, okay, where's the point cloud? And what you see here is the path walking front and back. And in the end, we see 17 meters drift. We see 17 meters difference between forth and back. And this is a large amount, and this also might happen in the city, and we see that this also happens in the city for mobile platforms, so we need to tackle this. We somehow need to reduce this, otherwise we have problems. And this is done with an up-to-date scanning system. And the reason is the georeferencing. So what we need to do? We need to tackle this by developing certain algorithms. And this exists in Höllental climb, this exists also in some other applications. If we do monitoring of factories, we also have mobile platforms that walk across the factory, and now we want to document what changes in the factory. And we have uncertainty here. And what can we do with this? What is our strategy to tackle this in the factory, but also in the city, as I will show afterwards? We tackle this with, well, we say, okay, we have the data that we collected, and we need to somehow fragment this data. We need to bring this in small planar or in small parts. And then those parts that we fragment, we need to consider individually. And in this analysis here, we just wanted to find out, okay, how accurate is this data? So we developed a strategy to quantify the uncertainty of mobile mapping data. And this we later use for the city, as I will show in the second aspect. So we have here a strategy with those 3 steps that you can see here in more detail, but which is not so relevant right now. But we use this to quantify uncertainty. And if we use one data set, here's one data set where we use this mobile platform here with this laser scanner, and then we want to find out, okay, how accurate is this? And with this fragmentation, just one example is we see that there are certain errors, so that we have drift effects in certain errors, and those we now need to reduce. And we need to find a strategy to reduce this. This is what we will do in the city. So this was based upon plane matching on quite regular techniques, but we are also right now working on using deep learning and machine learning to tackle this. And we have here a certain strategy, and this is just one example and one result where we see, okay, we can quantify the uncertainty with this quite well. Not perfectly, but we are on the right way to also use deep learning to automatically determine uncertainty of a point cloud without having ground truth. This is the important aspect. We are working on doing this without ground truth. So we have a method and a workflow to quantify uncertainty. But can we also align point clouds in the city? And we have here an example where we say, yes, we can, using this strategy. So what you see here again is part of Munich. And we now have a new point cloud. This is on the left side, can be seen here on the left side. This is a new mapped point cloud from a mobile mapping system. And now the task is to integrate this into the existing geodata. But we have, as I mentioned, those drift effects, and this does not fit. So what do? We say, okay, based upon the knowledge from before, we fragment this data. We bring this into small blocks and try to register individual blocks, keeping consistency between those blocks still. And the problem is now, we could do this theoretically, but the blocks need to have a certain geometric richness, otherwise it doesn't work. So we thought about how can we determine geometric richness to bring the point cloud into fragments that make sense geometrically so that we can accurately align them to the city model or to the point cloud that already exists. So we have a certain method that tells us now, okay, here need to be larger segments, here can be shorter segments. So the segments are adaptively determined based upon geometric richness. And each of these segments now has enough geometric richness. You can see a point cloud above, in the middle and down. Those are the 3 blue examples, and though all have enough geometric richness to be able to be registered. Now we have blocks to be registered, and we need to think about how to register them, keeping in mind what I said before. We have outliers, we have disturbing information, traffic, and all this kind of stuff. So generally there is something that we would use, a GICP, but we found out that this is really not enough. We need to have some other strategy, and this is where we came up with using something that is called plain voxel GICP. So we find planes in the city and then use them to register on the point clouds. And then we have also certain conditions that the planes need to meet, and then in the end it works. And if we somehow all bound this together to a workflow, we say, okay, we have the source data set, the new mobile map point cloud, then we have the city data set, we pre-align them, then we do the fragmentation, and then we use the ICP and the derived new method of the ICP to, in the end, have a good registration of the point cloud. And we can do this across various data sets. We used lots of data sets in Munich to improve this method and also to use this method. So you can see here some examples before and after registration. Here are also some numbers. So we can achieve really high accuracy with this method compared to the state of the art. But clearly this depends also on the question, where do I align to? So do I use airborne and mobile mapping data? Do I only use mobile mapping? Do I only use airborne? So depending on the perspective of the given information, this works better or not so good. But in the end, the method is able to do this. And this workflow that we developed ended up into a software that is not yet published, but that will be published in the next week. So there is an open source software that you can use to integrate new mobile mapping laser scans into your existing geodata from the city. And there will be some information the next weeks where to download this. So this we did in the collaboration with City of Munich, and this will be free to also other people that are interested in this. So this is how we align to point clouds. But can we also align to LoD2 City Models? And why is this maybe a separate topic? So it's a separate topic because if we align, or if we want to georeference on LoD City Models, we also need to tackle the fact that the LoD City Models do not reflect reality in all cases, but we have model uncertainty. We have uncertainty in the LoD City Models. And this also in collaboration with Tum, chair of geoinformatics. So what is the problem statement? The problem statement is we have point clouds. They should reflect reality quite well, despite noise and stuff. And we have models. And those models are always, as every model is, simplified. So we have parts in the model that are not reflecting reality. We have here, for example, many buildings, as you can see here, that have a wall plinth. So we have survey footprints that document the vertical wall of the LoD2 model. And we have the reality that looks like this. And if we now make a point cloud of this building and want to register this point cloud to the LoD2 city model, then we don't tackle the fact that we have here this wall plinth and diverging information vertically. So we somehow need to consider the information from the city model differently depending on the height and depending what is represented. And we can do this also coming up with a strategy where we say, okay, we have our point cloud, we have our LoD city model, and now we want to align them to each other. This in the end works out, but only if we apply a certain method in between where we say, we look how well does it fit, where is the plane that I want to align, and then we tackle this differently. In the end, this works quite well. We document this also on several experiments, like we also used a building from TUM, we used the Pinakothek, we used some different street buildings, also curved buildings, also glass facades, and we found out that this works quite well. So only one illustration here, we have a building, we have state-of-the-art methods. These are all state-of-the-art methods. The method I propose here is called LM2Rec, and if we compare here, this fits quite well, this LM2Rec, compared to the other methods. So we also showed and validated that this works quite well. And we would have several examples where I could prove this. So, in the end, I wanted to talk about integration of updated laser scans into as-built point clouds for urban digital twins. And the first statement was, okay, we need to have up-to-date urban digital twins. So we need to do rescanning, and this rescanning needs to be integrated into the information. And to be able to do this, we need point cloud processing, not only point cloud mapping, so measuring, but also processing the data. And this process needs to reduce and estimate the point cloud uncertainty to be able to validate it and to be able to say, okay, where do I trust my information? We need to distinguish between relevant and irrelevant information if we want to align to given information. And we need to integrate point clouds into existing geodata. So point clouds, city models, maybe also BIM models, maybe urban digital twins, and therefore we need to tackle all those aspects. So this can be used to transform the data. And now once we have registered the data, georeferenced the data into existing data, then the next step would be that I will not cover today is, okay, now we have information registered, and now we have information that might not agree with each other. So how to use this disagreement and which information to trust more to decide, is the new scan accurate or is the given information accurate? There we are working right now on methods to validate this. So this will come up next. And those are the references if you're interested. And that's all from my side. Thank you.